Hi, in this video we are going to study the calculation of the Fourier series coefficients of a pulse train. Now our periodic signal is obtained by the periodic repetition of a rectangular pulse. Now the rectangular pulse is the following signal. Okay, the graphical representation is it has a duration equal to say t cap, so it will be non-zero from minus t cap over 2 to t cap over 2, and its magnitude will be equal to a. In other words, the expression for p of t, the rectangular pulse, is a for t between minus t cap over 2 to t cap over 2, and it will be 0 otherwise. Well, from the graphical shape we see why we call it the rectangular pulse. Now, so t cap here is the duration of the rectangular pulse. Now let us obtain a periodic signal by using this p of t by repeating p of t with a period, fundamental period, equal to t0. So x of t will be defined as follows: m from minus infinity to plus infinity, p of t minus m t0. Okay, and we choose t0, the fundamental period, greater than the duration, so that in the periodic repetition of the rectangular pulses, they will not overlap. Okay, so the graphical, if we draw the graph, our x of t will be the periodic signal, which is obtained by repeating the pulse, rectangular pulse, with a period t0. So this is minus t0, and we will have, of course, the periodic signal obtained by the repetition of these pulses. So this is the 0 point, and this is a. Well, it is clear that this point here is t cap over 2. For example, this point here is t0 minus, okay, let me write it like this, t0 minus t cap over 2. So this, from this picture, it is clear that if t0 is greater than t cap, they will not overlap. Okay, now x of t is periodic with period capital T0. Therefore, x of t will have a Fourier series representation given by the usual expression ak e to jk omega 0 t. So we write down x of t as a superposition of complex exponential signals which are harmonically related. The frequencies are integer multiples of the fundamental frequency omega 0, where omega 0 is related to the period of our signal x of t by means of this expression. Omega 0 is equal to 2 pi over t0. Okay, now the coefficients can be calculated by using the formula 1 over t0, the integral from an arbitrary t0 to t0 plus capital T0 of x of t e to minus jk omega 0 t integrated with respect to t. Okay, how do we choose t0? Now, the most convenient choice is from, we can integrate from minus t0 over 2 to t0 over 2. Now, if we look at the periodic signal graph, minus t0 over 2 is this point, and t0 over 2 is this point. So we integrate over this interval from minus t0 over 2 to t0 over 2. So 1 over t0 from minus t0 over 2 to t0 over 2, x of t e to minus jk omega 0 t integrated with respect to t. Now here, if we look at the value of the function within that interval, in that interval the function is x of t is non-zero only over the interval from minus t cap over 2 to t cap over 2, and the value of the function over that interval is a, e to minus jk omega 0 t integrated with respect to t. So we have this integral. Now we have a over t0, and we have the integral of the complex exponential function e to minus jk omega 0 t divided by minus jk omega 0 evaluated at minus t cap over 2 and minus t cap over 2. Okay, now we are going to substitute these values and try to obtain a neat expression by means of certain substitutions, identities, etc. So let us now do that. Okay, we have evaluated ak as a over t0 e to minus jk omega 0 t divided by minus jk omega 0. Okay. Evaluated at t cap over 2 minus t cap over 2. So this will be equal to a over t0 e to minus jk omega 0 t cap over 2 minus e to jk omega 0 t cap over 2 divided by minus jk omega 0. Now, if we look at the expression in the numerator, we see that it is related to the sine function. In fact, it is equal to a over t0. What is it equal to? It is minus 2j sine k omega 0 t cap over 2 divided by minus jk omega 0. Why minus sine here? Because we know that sine k omega 0 t cap over 2 is equal to first this term e to j k omega 0 t cap over 2 minus this term. Therefore, we have a minus sign coming from that. Now here we say that these j terms will cancel out, and also the minus signs will cancel out. And we have a sine k omega 0 t cap over 2 divided by t0 k omega 0. Now, here we can do the following. We know that omega 0 is related to t0. Omega 0 is equal to 2 pi over t0. So we substitute this value now in this expression and we obtain a sine k 2 pi over omega 0 t cap divided by 2 2 pi over capital T0, because we are substituting omega 0, 2 pi over T0 t cap divided by 2 divided by T0 omega 0 is 2 pi, therefore we have 2 pi k. T0 omega 0 gives us 2 pi. Okay, here we have a cancellation of 2, the terms 2. And therefore we have okay, I think I have forgotten this 2 factor here. So there is also a 2 over there. So we have 2a, and therefore these two, those 2's will cancel out. And we have therefore a sine k pi k t cap divided by t0 divided by pi k. Now, in the argument of the sine function, we have the term pi k, which is also in the denominator, but we have also in addition t cap over t0, and t cap over t0 is a meaningful value. It is the ratio of the duration of the rectangular pulse to a period, to the fundamental period. So let us divide and multiply by t cap over t0. So we have the following expression for ak. ak is equal to a t cap divided by t0 sine pi k t cap divided by t0 divided by pi k t cap divided by t0. So we have sine of a certain expression divided by that expression. So in fact we have evaluated the coefficients, but this expression here has a certain special name as a function, and it is called the sinc function. So we define the sinc function, okay, as sinc of, for example, t, let us say, it is sine pi t divided by pi t. Now graphically, the sinc function is exhibiting an oscillatory behavior as follows. This is the sinc function. It has zero crossings, and these zero crossings are at 1, 2, 3, 4, etc., and minus 1, minus 2, etc. But since we have t in the denominator, for larger values of t, the value of the function decays to 0 eventually. Now, if we compare the definition of the sinc function with our expression for the Fourier coefficients of the rectangular pulse train, ak, the coefficients turn out to be a t cap divided by capital T0 sinc k t cap over T0. Okay. Now, finally, we have obtained a very neat form of the expression of the Fourier series coefficients of the rectangular pulse, because here we see the ratio of t cap to T0 as the multiplier of the sinc function, and also as the argument of the sinc function, we see the same ratio, t cap divided by T0 multiplied by k. So for larger values of k, in the positive sense or negative sense, this means those are the coefficients of the high frequency components. Because of the decaying behavior of the sinc function, the high frequency components will have smaller values of ak. The coefficients will eventually tend to 0 as k tends to plus or minus infinity. Now, if we compare this Fourier series representation of the periodic pulse train with the Fourier series expansion of the periodic impulse train, in the impulse train, we remember that the coefficients are all equal to 1 over t0. All frequency components are represented equally. And remember how we interpreted that result. That result is due to the singular behavior of the impulse function. But here we have a rather well-behaved pulse. The rectangular pulse is not a singular pulse. It has a finite value over the interval from minus t cap to over 2 to t cap over 2. And therefore, high frequency components eventually, the weights of the high frequency components eventually decay to 0. Okay, thanks for watching.